Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we will be looking at the mechanism by which alkenes react and then examining some of the reactivity of alkenes. Now, unlike what we have examined so far, alkenes do not have a delta plus on the molecule that will attract nucleophiles. An alkene possesses a pi bond, not some electronegative atom. The pi bond is diffuse, containing electron density. If you like, there is a sigma component. And then you have this side-to-side overlap region above and below the plane of ring, which is delta minus, or shall we say, electron rich. This pi cloud of electrons will not attract nucleophiles. Negatively charged molecules or groups will be repelled by the negative charges on the pi cloud. In fact, what's going to be attracted are species that seek out electrons, or what one might refer to as electrophiles, and I'll just label it as E. Electrophiles need an empty orbital. They may even have a positive charge that will help attract them to electrons. The electrophile will attack, drawing the pi electrons, and when the molecule attaches with the E, it will pull the pi electrons away from this carbon, making this carbon electron deficient and now positively charged. This we've seen before. This is a carbocation. And so all of the chemical behavior we expect of carbocations will occur here. And so what's attracted to carbocations now are nucleophiles. They may be negatively charged. They can be neutral, but they have a lone pair of electrons. And if the nucleophile comes in, then you've ended up adding both an electrophile and finally a nucleophile. Now, the pi bond ends up being converted into two sigma bonds. Well, what is going to be the slow step in this reaction? Clearly, the slow step in this reaction will be the formation of the less stable. Here we're forming a stable molecule. This is going to be fast. Nucleophilic attack. But the initial electrophilic attack is going to be slow because you're forming an unstable intermediate, a carbocation. What will control how fast this slow step goes? Well, what will control the speed of the slow step will be the stability of the carbocation. Actually the transition state, but as the E plus adds, there's carbocation character in the transition state. So anything that stabilizes the carbocation will speed up the reaction. It turns out electron donating groups, such as carbon atoms, here and here, will pump electrons into the alkene, increasing the delta minus, speeding up the E plus attack. The inductive electron donation stabilizes the carbocation, making it faster. So electron donating groups, if you like, on the alkene, electron donating groups speed up the reaction. Increase reactivity. Okay, electron donating groups increase reactivity. This is simply because inductive electron donation stabilizes the carbocation and so it forms faster. However, if we change this, for example, perchlorines, which are electron withdrawing groups, would effectively make the positive charge larger on the carbon, destabilizing the carbocation. So electron withdrawing groups such as highly electronegative groups will decrease reactivity. Okay, chlorine, which is extremely electronegative. And this is simply understood either by looking at the reaction initially. What attracts E+? Well, delta minus. Electron donating groups will increase the delta minus in the pi cloud, or one can rationalize that as occurring. Electron withdrawing groups will reduce the amount of delta minus. More delta minus attracts E+ faster. Less delta minus attracts E+ slower. Now, you could look at it from the perspective of the product intermediate. If you have inductive electron donation, the plus becomes smaller. It becomes more stable. The charge gets spread out a little bit, out onto the carbons. This inductive electron donation stabilizes the plus. It forms faster. Electron withdrawing will put more positive charge on this carbon, destabilizing it, making it form more slowly. What about the direction? What if we have an alkene that's asymmetrical, such as this guy? Well, if you have an asymmetrical alkene, what kind of electrophiles can we react it with? Well, what would be the simplest of electrophiles? A positively charged species that's simple, that we've used a lot. Well, it's acid, H+. A nice example of an electrophile could be H+. What is an example of a good nucleophile that we've used a lot? Well, an example of a good nucleophile are the halides, X-, where it's chloride, bromide, or iodide. What would happen if we tried to do this reaction, say, with hydrogen chloride, hydrochloric acid? Well, we get a two-step reaction. H+ would add first, and then the Cl, and we'd end up putting H and Cl across where the pi bond was. So I could envisage it adding this way. Or I could also envisage the reaction where it adds the other way. The Cl adds here, and the H goes the other way. At first, you would think both products are possible. But the answer to which product forms actually depends on the carbocation. See, all our rules for carbocation formation apply. For example, in the SN1 or E1, in which you form carbocation, you were instructed to always draw the carbocation and look for 1,2 shift. You'll notice I drew my products without worrying about the carbocation or examining it. So let's draw the carbocation. Let's consider what carbocation would form to make the top product. Well, if I was going to make the top product, the H plus adds to the middle carbon. So let's do that. Let's look at this carbocation. If the pi electrons grab the H plus, so the H goes here, before the chloride attacks, I would get this carbocation. Well, there's a carbocation. What kind of carbocation is it? It's a primary. What do you know about primary carbocations? Primary carbocations are extremely unstable. If they form, you get a 1-2 shift, certainly to a secondary. But let's look at what kind of carbocation would form to make the bottom molecule. Well, here the H added on the end, so I'd have CH3, CH, CH2. The H would add here. And what do I get here? Positive. What kind of carbocation is this guy? He's secondary. That's a secondary carbocation. You could form a secondary carbocation, you could form a primary. Well, who's lower energy? The secondary carbocation. You don't have to worry about a shift. If your pathways, one pathway is primary carbocation, another pathway is secondary carbocation, primary carbocation formation is so high energy, it's not going to happen. This pathway will not occur. So you won't get shifting. The H plus will add to the carbon that will yield the most stable carbocation, the secondary. And what happens? This guy does not form. Only this guy. Why? Because you have to go through a primary carbocation to get this, and it's too high energy. Now, when this was originally developed, it was not well understood, the concept of carbocation stability, and hence it was reported as where the electrophile attacked. And this was done by a Russian chemist named Markovnikov. Now, Markovnikov reported that the electrophile, or the H plus, will add to the carbon of the double bond that possesses the most hydrogens. And indeed, that appears to be the case. The H plus added to the CH2 of the double bond, not the CH. It added to the carbon of the double bond that has the most H's. So this H going on the CH2 is said to follow the Markovnikov. Now there are different ways of writing his name. It's reported as Markovnikov, Markovnikov. We'll just go with Markovnikov. Markovnikov orientation simply is the electrophile adds to the carbon with the most hydrogens. This occurs because it yields the most stable carbocation. Our reaction mechanism allows us to understand why this occurs. If we get anti-Markovnikov or some deviation from this, we must explain it mechanistically by looking at the specific reaction mechanism for each case. Another thing we have to be concerned with in the reactivity of alkenes is stereochemistry. And one example of where stereochemistry is important is how the groups add. Now, in many molecules, it's not obvious, but if you use an alkene like cyclohexene, we can do reactions where it's very important that you take into account the stereochemistry of the product. The only way to do that is to examine the mechanism and try to explain the experimental observation. Let me explain what I mean. Putting dots so you can see this is a 6-carbon cyclohexene. Let's try a reaction where we use KMNO4 and we also use hydroxide. And we're going to use it cold and dilute. If you do this, you will add OHs to our alkene. But you will get a cis diol. This is referred to, if you get a cis-only product, this is referred to as syn addition. Or if you like, addition to the same side. The electrophilic addition goes syn. If we get syn addition, cis-only products, we have to look at the mechanism of reaction in this case to explain it. And so when we actually get to this reaction, examine it, we will do that. But we could also envisage some reactions where you don't get cis-only. This occurs when you use Br2 with, say, carbon tetrachloride. CCl4. This carbon tetrachloride is my solvent. It doesn't really participate in the reaction. I'm just using it as a solvent. Often this reaction is conducted in the dark to prevent free radical side reactions. What happens is the bromines add across the double bond. But guess what? In this case, the addition. That's right. Is trans. We get trans product only. This is called anti-addition. So we must understand the mechanisms by which KMNO4 puts OHs on an alkene and by which Br2 puts two bromines on an alkene, and the differences that account for why in one case you get syn addition and why the other case you get anti-addition. So when we actually look at these reactions, we will be examining the mechanisms to explain the stereochemistry of the addition. Now, as usual, if we examine the general reactivity of the alkene, once again remember that the alkene is the functional group of the molecule. That is, it's the atom or group of atoms that define the structure of a particular family of organic compounds and determines their properties. It is that structure within the molecule that represents a site of reactivity. The reactivity occurs because the pi electrons tend to be more diffuse. P orbitals are more diffuse than the s, and they're less directed. The side-to-side overlap allows mutual repulsion of electrons to push the orbitals out. This makes the electrons in the pi cloud available to the electrophile. Well, we've mentioned H+, and we're seeing some other groups here. What are the examples of electrophiles, or what can be a legitimate electrophile? Well, our electrophiles can be, obviously, if we've used H+, They can be positively charged reagents. Positively charged reagents such as H+. We could also use carbocations. If we could make a carbocation like methyl plus, I admit methyl's even higher energy than a primary. If we could make CH3 plus carbocation, it would be very reactive. It would be a powerful electrophile. It's high energy. It wants its electrons. This would react very quickly with alkenes. So any carbocation like methyl plus, terbutyl plus, would be a potential positively charged reagent, a potential electrophile. We also have the possibility of neutral reagents. In our syn and anti-addition, we had neutral reagents there involved in reaction. Well, neutral reagents can come in two forms. We can use Lewis acids. Lewis acids are electron pair acceptors. They are able to accept electrons. They can accept electrons. Why? Because they have empty orbitals. Now, examples of these, of course, are AlCl3, BF3, BH3, and others. Another example of neutral reagents are polarizable molecules. Polarizable molecules. These are molecules such as Br2, Cl2, I2, large molecules. Bromine and iodine be more polarizable than chlorine, but the larger and more polarizable they are, the more they're able to interact with the pi cloud. And we'll look at how they can play as electrophiles. The third group, of course, are metal ions. They are Lewis acids because they are ionized, they have empty orbitals. Because like Lewis acids, they have these empty orbitals, molecules or ions such as silver plus, mercury, 2 plus, platinum, 2 plus, can act as electrophiles. Okay, now in our characteristic reaction, if we focus at or focus on a reaction where we attack an alkene, we've already seen that it involves the attack of an electrophilic component and then a nucleophilic component, those two often forming a single molecule like HCl. Well, based on this and what we form, we can very quickly come up with an idea as to whether these reactions are exothermic or endothermic. For example, in order to do this reaction, I must break a sigma bond, an XY bond. I must also break the pi bond, which is the side-to-side overlap of the two p orbitals. Now, this side-to-side overlap is not as efficient as the directed sigma overlap in the XY bond. Side-to-side overlap is less efficient, and inherently pi bonds are weaker. Now, to break bonds, I must put in the bond dissociation energy. But breaking a single sigma and one pi requires less energy to be put in than forming two sigmas. Notice on this side we form a CX and a CY bond. So we're getting two sigmas. That will release energy. Two sigmas will release more energy than we have to put in to break a single sigma and a pi. And because of this, most of the time, these types of reactions are exothermic. Delta H is negative. So addition to alkenes produce more stable molecules and release energy. Well, let's focus more closely on the reactions with HCl, HBr, and HI. Now, HX can be used by dissolving the hydrochloric or hydrobromic acids in acetic acid and reacting with the alkene, or you can bubble HCl gas right through the alkene itself. Interestingly enough, HI is such a powerful acid, it's usually prepared in situ, which means actually in the reaction tube in the situation you find yourself in. We don't go to a bottle and get HI very often. Usually you make HI by reacting potassium iodide with phosphoric acid. And the HI will form and be used in the reaction. Now, HCl and HI always only give Markovnikov addition. What's Markovnikov addition again? It's the addition of H plus to the carbon of the double bond that has the most hydrogens. And you only get that. HCl and HI give Markovnikov addition only. But HBr doesn't do that. If you have an asymmetric alkene, and you react it with HBr in the dark, you will get Markovnikov addition. Remember, Markovnikov addition puts the H on the carbon with the most hydrogen, so I'm going to get CH3 here. And the bromine will add to the other carbon. But if you use HBr in the presence of ultraviolet light, and I'll use H nu to symbolize ultraviolet light, this is the Greek letter nu, or instead you add peroxide, hydrogen peroxide, either one of those, you can get anti-Markovnikov addition. where the H adds to a carbon with the least number of hydrogens. So the Br goes here. Well, this clearly begs explanation, and in order to do this, we have to look at the mechanism. Now, we've already looked at the mechanism for pathway 1. In pathway 1, we're doing electrophilic addition. We go through a carbocation. But pathway 2 is different. It is not electrophilic addition. Let's take a closer look at what happens in pathway number 2. In pathway number 2, we have ultraviolet light, which will split the HBr, or we use peroxide. These reactions are referred to as initiation reactions. If you use peroxide, and in the presence of any light or a little bit of heat, the molecule falls apart very quickly to two HO dots. It's a radical mechanism. HO dot can react with our HBr and produce H2O and Br dot. This prepares a radical. Now, the concentration of radical at any given time in solution is very small, but it is crucial to causing the chain reaction or the propagation steps to occur. Chain reaction, or what is often better called the propagation steps. How the reaction propagates itself. Okay. Well, how does it occur? Well, let's take our alkene. And have the Br dot attack it. Now, Br dot is a radical. It would prefer to have an electron and become Br minus. Okay. It would prefer to make a bond. And by sharing electrons, achieve a filled octet. It sees available electrons in the diffuse pi orbital. You know, we have this 2p orbital here. And we have our electrons. Opposite spins in the pi orbitals. This Br dot can actually add to one of those electrons. If this electron couples with this one, that's going to leave this electron all by itself. And so you can get CH2 and the Br combined, but that's going to leave a dot here. Now one might ask, well, why didn't the Br go with the middle radical? Why didn't it add here and you put the dot on the end? The answer is fairly simple, in that radicals have stability similar to carbocations. It's a little less easy to understand, but essentially, secondary radicals are more stable than primary radicals. And so the Br radical adds to the carbon with the most hydrogens. Radical addition is not referred to as Markovnikov orientation. We don't use that terminology. Now, what's interesting is if you are comparing a secondary carbocation to a primary carbocation, Likewise, the secondary radical, so I'll put secondary dot, is more stable than a primary dot. But what I've done here is show you that the energy gap is smaller in radicals. This concept's important in order to understand why here, because of a huge energy gap, there's enough energy to allow 1,2 shifting. Here, we don't have to worry about rearrangement. The energy gap is too small to account for 1,2 shifts. And so shifting's not really a concern in radical cases. All right. So secondary radical forms because it's preferred over primary radical. But the energy gap isn't so large, and so because of that, I don't have to worry about looking for 1,2 shift. All right, let's continue. This radical can now react with HBr the dot grabs an H dot, and that will leave a Br dot. The reforming of the Br dot allows a chain reaction to take place where the Br dot goes back to the beginning and the first step happens again. And you keep this chain reaction cycle going until you use up radical. Radical can quench itself in a variety of termination steps, but these termination steps don't happen very often because the concentration of radical is very small. Let's take a look at the overall, sorry about that. Overall reaction, if we add these up, this is just alkene up here, so let's fix that. We use fish hooks for single electrons, not full-headed arrows. Show how the electrons separate. So we have alkene. If we add this up, we have HBr. We have a radical. And we have the Br dot from up there. That, all here we've got, gives us CH3, CH2, CH2, Br. We have plus the radical. Plus Br dot. Now, identical groups on opposite sides of the equation can be subtracted out. They cancel. So the alkyl radical cancels, the Br dot cancels, and because they cancel, I can remove them. So all I'm left with is the overall equation, which is the alkene reacts with HBr to make Antimarkovnikov 1-bromopropane. Wow. The chain reaction, which is better referred to as propagation. The propagation steps. Now, the last steps which destroy the reaction and end it are called termination. In a radical reaction, termination steps, such as two bromine radicals crashing together, would kill the reaction because no bromine radical would be available. That would produce Br2. You might have the alkyl radical, CH3, CH dot, CH2, Br, crash into a Br dot, and you get CH3, CHBr, CH2Br. And there are other ways radicals could couple or even possibly disproportionate. So there's a variety of termination steps that could occur. These reactions happen slowly over time, and they are the reactions that require a certain amount of peroxide or ultraviolet light to continue the radical production and keep the relative reaction rate up throughout the duration of the reaction. The concentration of these products in the termination steps are very, very small. The bulk of the product goes through bulk of the reagents go through the propagation steps. Now you might notice something interesting here. I'm going to wipe out the title and the top initiation step. And you might say, wait a second, Dr. Lloyd. I remember some stuff that we covered in resonance. I remember something about allylic groups and allylic positions being relatively reactive because of resonance. Why did you have Br dot go for the pi bond? Why didn't you have the Br dot grab an allylic hydrogen off of the sp cubed carbon next door to the double bond? And then make HBr and CH2 dot. Now if you spotted this, you're quite observant, because really this should be favored because the radical is resonance stabilized, isn't it? The pi bond and the electron can couple, and this will put an electron out on the other CH2, and you get resonance stabilization with the lone electron spread out over two carbons. Wow. Doesn't that happen? In fact, it does. But you have to ask yourself a question. Where does this radical go? I mean, the second step in our reaction down here is the alkyl radical attacks HBr. Oh, good, we got HBr, we got HBr reaction, so he attacks HBr. What did you pull off? An H. Okay, so he can pull off an H. Wait a second, if I pull off an H, that'll just go backwards. He can form, but he'll just grab the H and go back to this guy and give me my starting material and Br dot. In other words, yes, this probably happens. It probably happens rapidly. There's probably a bit of a allylic radical floating around, but it doesn't go anywhere in this reaction. In this reaction, the allylic radical would just grab an H dot and go back to my 1-propene. So this happens, it goes back and forth, back and forth, back and forth for quite a while, until Br dot accidentally goes for the pi electrons. When that happens, he can react with HBr and make bromopropane. So in this case, yes, the formation of an allylic radical can happen, but it doesn't get you anywhere. So if later on you notice sometimes my radicals seem to attack the pi bond, sometimes they attack the allylic position, well, the truth is the allylic position is probably favored, but sometimes it'll lead to product, sometimes it doesn't. When it doesn't, the reaction will keep going till something else happens. So this reaction is, because it's an equilibrium, just gives you back the Br dot, which will eventually attack the alkene. Now get this, it might affect the rate, but it really doesn't affect the reaction outcome. Okay, why do we get Antimarkovnikov? Why, when HBr is thrown in the presence of peroxide, is Antimarkovnikov addition observed? Well, in this case, the most stable radical is formed when the Br adds to the carbon with most hydrogens. It looks Antimarkovnikov if you consider electrophilic addition, but this is a free radical mechanism. It's not electrophilic addition. There's no electrophilic attack taking place. It's radicals. And so it's a completely different reaction mechanism. Okay. I think that's an excellent place to stop. We'll continue with this reactions of electrophiles on alkenes with our next Scribblecast lecture. I'm Dr. Brian Lloyd. This is my Scribblecast lecture. Thank you for listening.